Good afternoon or good morning, ladies and gentlemen. Thanks for coming to this seminar. Today we have a seminar to be presented by Martin Henke, who is a postgraduate student at UAA in the College of Engineering. Martin completed his bachelor's degree also at UAA, and after that he served within the Peace Corps in Tanzania, and he returned back to UAA to pursue his master's degree in mechanical engineering. He's currently finishing his master's thesis, and his studies and research is focused on fluid dynamics, CFD, and convective heat transfer studies, numerical methods, and analysis of heat transfer and thermal management in batteries. Following his completion of the thesis, he plans to attend his PhD. He has been already accepted in one of the East Coast universities, one of the best universities in the East Coast. So yeah, he's preparing for the journey as well. So please welcome Martin Henke.
Thank you, Dr. Hailu. You took some content from my first slide, but that's fine. I'll zoom through it. But today my presentation will be on the investigation of active air cooling designs for stationary battery systems. And I think that probably requires some explanation. I'll be getting into that, but yeah, I'll be moving on to my first slide. And let me make sure that everything's going well. There we go. So background, a little about me. So as Dr. Hailu said, I got my bachelor's degree from UAA College of Engineering in ME. I'm a lifelong Alaskan, and following my bachelor's degree, I went and served in the Peace Corps in rural Tanzania for 2 years. But really academia, and more specifically engineering, was calling me, and I ended up coming back to get my master's degree, and that's ongoing. I'm hoping that if everything goes well, I'll be graduating next month. So my areas of study are in fluid mechanics and dynamics and numerical methods, and my research really is the synthesis between the two in CFD and convective cooling. And then my postgraduate activities, I think I'm one of the only presenters that isn't a professor, and as a graduate student here at UAA, I've had the opportunity to teach several labs, being intro to HVAC and intro to fluid dynamics, and that's been very rewarding as a student. I've learned a lot myself. And then also I got to work as a research assistant for Dr. Hailu, which I've continued that research on to today. So what are stationary batteries? I think getting into the meat of the presentation, stationary batteries really are exactly what they sound like. They're batteries that aren't moving. They're non-portable, and they're used for a variety of different uses in different industries. I'll be getting into that in a moment. So one of the primary uses, and a use that they've been used for many decades for, is interruptible power supplies, and that's UPS. So these type of systems are meant to provide power in case of any interruption from grid stability or anything else. So what they do is, implemented into a system such as a server system or a industrial process. It maintains power for those systems and prevents any downtime or crashes happening for these systems. And then there's energy storage, and this is really emerging over the past few decades with the implementation of renewable energies that happen to be intermittent in their nature. So any renewable energies such as solar, which generate power during the day but don't at night, there needs to be some form of energy storage that accompanies that in that renewable energy. And batteries in the past few decades have really come into their own as a viable method to accomplish energy storage. So why, and of course, stationary batteries are a form of electrochemical energy storage, but what do they bring to the table? Why are they being used for this? So one is rapid discharge, and this is what makes them special and especially good for UPS systems. that rapid discharge allows for prevention of a interruption event in the power systems versus looking at other forms of energy storage, such as hydro or pumped hydrogen or anything else. These take minutes or even longer to come online versus batteries are instant. They have relatively low implementation costs compared to other technologies, and it depends on what technology you're comparing it to. But looking at something like a large-scale hydroelectric energy storage program or system, these systems are relatively cheap, and they're also very modular, and they can be scaled and changed very easily. So even post-implementation, these batteries can be scaled up, scaled down, changed, and that's a major advantage that they bring to the table in comparison to some of these other systems, which are more set, primarily hydro or pumped hydrogen. And then lastly, and this is a rather new one, high round-trip efficiency is with the advent of lithium-ion batteries, the round-trip efficiency of energy that is put in and then able to be extracted is around 99%, which is extremely high, even in comparison to some of the best technologies. And so lithium-ion batteries have brought this advantage to the forefront of the technology, but it is shifting. So this is a field that is changing a lot in the previous and currently. So they're increasingly prevalent in modern power systems. So modern power systems being further and further reliant on computational processes or servers or telecoms. Really, all these types of systems are very vulnerable to even slight interruptions in power. So the use of UPSs for telecoms or anything dealing with computers really is increasing, but even with the implementation of more and more renewable energy, wind and solar are both intermittent and require some form of energy storage, and batteries are being used for these purposes. There's also a shift going on in that previously lead acid batteries were considered the optimal way to achieve one of these systems, but lithium ion, with plummeting prices in the past decade, has really come to the forefront of the stationary battery technology, and they're currently being used in most energy storage systems are using lithium ion now because of that high round trip efficiency, but even some UPS systems are beginning to use lithium ion technology. And then lastly, power demands for these systems are increasing. It sounds banal, but as a society, we're becoming more reliant on power and power systems. And as this reliance increases and the demands increase, so do the demands that these systems have to output. So getting into what I'm actually studying is heat generation and cooling. And batteries can generate a lot of heat in operation. And we're all familiar with this, but you'll notice that I said operation. I'm not talking about charging or discharging or even in standby, because all three of them produce heat for a stationary battery. So stationary batteries, even when they're not being used, they're hooked up to a power supply to remain at full charge. And during this time, they're producing heat. And as they produce heat, there's, of course, an associated rise in temperature. And I'll get to that in a moment. But some of this heating comes from irreversible heating, which is related to ohmic or internal resistance or activation energy in the chemicals going in the cell itself. And then some of it is related to reversible heating. Reversible heating is related to the entropy change in the electrodes of the battery. And this reversible heating, interestingly enough, can have an exothermic or endothermic effect. However, it's usually not the dominant source of heat generation within the battery. And so usually at very high current discharge rates, irreversible ohmic heating is the dominant heat generation source. So as I said, as heat is generated, temperature will obviously rise. And every battery is different, and it depends on the technology. Is it lithium ion? Is it lead acid? Is it nickel cadmium? But the general range that's given for safe operation operation of these batteries is from 10 degrees Celsius to 35 degrees Celsius. Lithium ion is renowned for being able to handle a bit higher temperature, around 45 degrees, and still perform pretty well. But this is usually the range that is considered safe. And what's interesting is as temperature increases, so does battery voltage and the battery performance. And if you're looking at this figure here, you'll notice that these are discharge curves for a lithium ion cell discharging at, I believe, 3 coulombs. And as it discharges for different temperatures, you see an increased voltage as temperature increases. And so really the performance of this battery is increasing with temperature. And so you might be thinking to yourself, well, that's great. Like let's run the batteries as hot as they can get. Well, there are some associated downsides. And there's the figure to show you and shock you how bad it can be. But elevated operational temperatures really cut back on the cycle life of these batteries. So cycle life is how many charge-discharge cycles you get out of one of these cells. And as batteries, if a battery consistently operates at a higher temperature, you're going to see that cycle life drastically reduced. And the battery will have to be replaced sooner. Certain technologies such as lead acid vented lead acid batteries produce hydrogen gas in operation. And while it's normally in very small amounts, that hydrogen gas evolution increases with an increased temperature. And obviously an accumulation of hydrogen gas could have explosive results. And so it's something to be avoided. Around approaching 55 degrees Celsius, there begins to be incidences of explosion or other unexpected failure that can occur, or catastrophic failure that can occur. And there's also the phenomenon of thermal runaway, which can result in the combustion of a battery. And this applies to, I believe, all cells, definitely lead acid and lithium ion. And this is a process, on the previous slide, you saw that as voltage increases, or as temperature increases, so does voltage. Well, as voltage increases, so does the rate of discharge, which results in more heat being generated and the temperature increasing. So it's really a positive feedback loop where the temperature results in a higher voltage results in a higher temperature, and these two spiral out of control until combustion or explosion can happen. And it's really the reason that you can't, you might have trouble receiving a lithium ion battery through the mail or something like that. And just an explanation of the figure, this is a fire that occurred at a cement factory in South Korea, I believe. And the source was traced back to I believe it was a UPS system consisting of lithium ion batteries. But we've had fires here in America. There have been several on the West Coast, and then there's been many worldwide. And oftentimes it's been traced back to lithium ion batteries or lead acid batteries. So stationary battery thermal management. Obviously, we've established that there is a need for thermal management of these systems. So these batteries are very big, and you might be thinking, well, you know, I don't have a problem with my car battery getting too hot. I don't have a, you know, if it's working correctly, my phone battery doesn't get too hot. Why do these need to be cooled? Well, while the surface area of these batteries is drastically increased because they're so large, really what's increased even further is the capacity and discharge rate capable in these large cells. And so it's really not comparable to, say, portable batteries, whereas these batteries have such high discharge rates that really natural convection or natural room temperature convection doesn't provide the cooling needed to keep these batteries within a safe range. Air cooling is really the only method of thermal management used for these batteries. And you may be familiar, some of the electric cars currently on the market are employing internal or external liquid cooling systems. And they're very advanced and very cool, but those do not really exist for these systems as it stands. That doesn't mean they couldn't be developed though. And then really the general approach that is taken to these batteries or these battery rooms is bulk room passive air cooling. And that approach treats the entire room that contains the batteries as a cooling space and just simply keeps it within a certain temperature range and allows batteries to naturally convect the heat away. So there's no forced air system being employed, and forced air, of course, being moving air being blown across the surfaces of the battery to further increase effective heat dissipation. There are some active cooling systems. Again, this is moving air. Some active cooling systems are implemented, but currently the standard remains to just place these batteries in a cold room. So motivation behind my research. The first is prevention of these deleterious effects that are related to high temperatures in batteries. And that's one, reduced lifespan. And then more importantly, I would say the safety incidences that can arise due to those elevated temperatures, which obviously is something that we want to prevent. But then continuing thermal management can be extremely costly for large stationary battery systems. Placing batteries in a room and then cooling the entire room is obviously not a very efficient system. And if you take into account the fact that these batteries are always producing heat, it really becomes evident that a huge portion of a large amount of energy every year is devoted to just simply managing these batteries' temperatures and doing it quite ineffectively. And then finally, there's been really a lack of research on how to effectively implement active cooling for the purpose of keeping stationary batteries cool. And there hasn't been much recognition that this needs to be done, or that there are, like I said, there's obviously very strong financial incentives to keep batteries cool and do it efficiently, but really no standards have been published. Research on the topic is absent, and really I want to lay a foundation for this field going forward. So my research focus, I'm only looking at air cooling systems. I'm not going off and developing a brand new liquid cooling system or a passive cooling system or anything new like that. I want to use air more effectively to cool these batteries and look at the resulting effects that happen. So my emphasis has been on studying methods to induce turbulence and better distribute air throughout an enclosure or a battery rack, and thus increase the heat dissipation. And I guess this is important, I should get into it now, but effective air distribution for an active cooling system is really important, because as these systems function, one of the primary reasons that they're not used is that it can lead to certain batteries being cooler than others. So if several batteries connected in series have different temperatures, and this is the term for this is a temperature differential along batteries, it can really damage batteries and result in several dying before they should. And in addition, there's also the phenomenon of spot cooling, where certain batteries have localized cool spots or gradients on the body. And this can also damage a battery. So there's a reason that active air cooling is, how should I say, has been avoided, because it requires proper design and implementation. Otherwise, it can harm batteries. And really, I need to account for that in my own research. Done that. So methods. 3 models were created, and each one has a unique design point that I wanted to investigate and how it affects the cooling of these batteries. And here you can see my model. These numbers assigned to battery assignments. I, of course, needed a way to assign some name or number to each battery, and you'll see that the batteries on the bottom are 1 through 4 and 5 through 8 versus the top are 9 through 12 and 13 through 16. And this is the default model. It consists of 16 batteries They're placed on a rack. They're modeled to be analogous to the actual geometry of one of these racks and these batteries that are used in stationary systems. And then they're placed in an enclosure. And the enclosure really is indicative of what an actual active cooling system would, how one would actually function. You'll see why, because it performs quite poorly. But air is basically vented into the bottom of the enclosure and then comes out through the top. The second model has attached vortex generators, and vortex generators are small fins that can be placed on surfaces, and their purpose is to disrupt laminar flow or developed flow and induce turbulence, mixing, and vortices into the flow. And in turn, all these effects will increase convective heat dissipation. And then lastly, there's a variation that uses a vent plate to cause small jets of air going through the case. And so again, this is just a plate mounted to the bottom of the rack. It's got small perforations in it, and the air shoots through those perforations and cools the batteries. Looking at the results and the effects that these different designs cause and contrasting the differences between the two, I can really assess which designs would show promise in further investigation and for cooling. Here are the two variants. The vented model is shown on the left. You can see the plate. I've made the rack transparent and I've removed the enclosures so you can see better. But the plate, you can see the small perforations there, and it's again mounted below that bottom rack. And then on the right, you can see the vortex generators attached to the arms of the rack. And there's a side view, so you can't actually see how they're lined up, but they are lined up. And then there's also vortex generators attached to the bottom of the rack to, again, disturb that incoming air flow. For analysis, I used computational fluid dynamics, or CFD. And if you're not entirely familiar with CFD, or I'll be getting to that in a moment, but for now, I'd just like to list out some of the advantages that it afforded me. One, it allows trials to be carried out quickly, inexpensively, and inlet input conditions to be manipulated fairly easily as well. I don't have to go down to the shop and switch out circuits or buy expensive new parts. I can quickly model them and run simulations through a computer. And then the second advantage afforded by CFD is that I can access results that otherwise would be extremely difficult to visualize or measure or see. And CFD really enables me to easily look at parameters such as airflow and visualize these kind of things. And you'll see why in a moment. So CFD, just giving a brief working definition, hopefully everyone is familiar with it. But if you're not, it employs numerical methods to solve complex, or in some cases, really impossible fluid flows. And so a numerical method, right, is assuming everyone has some background with math. I've included the figure in the top right showing a Riemann sum. And let's say you don't know how to analytically solve for the area under the curve. You can employ a numerical method, such as a Riemann sum, to manually solve for that area that is under the curve. And it's not a one-to-one comparison with CFD, but it does operate off a similar rationale or idea. So similar to the Riemann sum, the fluid domain is divided into smaller control volumes in the process known as meshing. And you can see in the lower figure, the air surrounding an airfoil has been meshed. So it's been divided up into smaller volumes, in this case areas. It's a two-dimensional analysis. And for each of those areas, numerical methods are applied to really solve for the bulk fluid flow through in an area. And really it allows me to model turbulence, heat generation, convection, and other physical processes like radiation. Natural convection can be accounted for, gravity, and many other processes. can be modeled through CFD, and it's really a powerful tool. However, so it's a powerful tool, but how do we know it works, and how do I know that it's valid? And the answer is I don't. Without some form of validation, CFD modeling really isn't defensible. So following the idea to use CFD modeling, a scaled down experimental model was created to be analogous to the default and vented models. And you can see here is the vented model. It looks slightly different than the previous models I've shown you. And you can see 16 batteries. Again, they're mounted on a rack. There's an inlet. The shape and geometry is slightly deviated, but not enough to be significant, I hope. And using the experimental model and the simulation model and comparing the temperatures that come from experiment with the temperatures that come from simulation, and looking for alignment between these two values is really the basis of validation and showing that simulation is a defensible or justified method of analysis. So here is the actual constructed experimental model. You can see it there. There's 16 batteries all hooked up to 6 car lights, which provided the load for them to discharge. The data loggers are shown on the right with 16 thermocouples all hooked up to each battery. And then there's a small fan that powers air and pushes it through the system. I spent quite a bit of time in the lab working with this, and lithium ion batteries were tested, lead acid batteries were tested. We have a huge box, you wouldn't believe how much it weighs, completely filled with small little 9-volt batteries that have been used and discarded. It's been quite an adventure working with these. But I was able to get what I deemed to be steady state temperatures from my data trials using these batteries. You can see that during a discharge trial, if you're looking at the x-axis, it's time in minutes. So for roughly an hour, I would record the temperature of these batteries, sampling every 30 seconds, and watch as they increased while discharging. And so that discharge is producing heat, temperatures are rising. You'll notice that they got up to nearly 50 degrees Celsius, which is pretty high, but not outside of the safe zone of 55, hopefully. I made it out alive, so that's good. But there's a lot of curves here, so I'll give some context to what's going on this slide. Batteries towards the front of the case near the inlet, namely 1 and 9, tend to be the hottest. You'll see why that is in a moment. Batteries 4 and 12 towards the back of the case, away from the inlet, tend to be the coldest. Batteries uniformly on the bottom tend to be colder than their analogous battery on the top. So 1 tends to be colder than 9, 2 colder than 10, 3 cooler than 11. That's the general shape of the data that you're seeing here. What's more important is that we recognize that at the spot where these curves flatten out, I have taken that as the steady state temperature, the final point where the temperatures have stabilized with the cooling system. So I use that in analysis. You can see here is my actual simulation. Before I said that batteries, I believe, towards the back of the case tended to be cooler, and we can actually see why this is using the simulation. You'll notice that batteries towards the back receive significantly more airflow, and that I'm sorry if I didn't explain, but air velocity is represented by the black mist that you see moving through the model. And this, again, is one of the primary advantages of CFD, is really, it would be very difficult to see this otherwise. So again, these batteries in the back of the enclosure are seeing a lot more airflow versus the batteries in the front of the enclosure. And again, this is leading to temperature differentials, which are extremely bad for the health of batteries in the line. And looking at the vented temperature model, this data looks much different. And obviously there's 2 main branches that the curves took. The lower branch quite simply corresponds to batteries that were on the bottom of the rack. So batteries on the bottom of the rack, 1, 2, 3, 4, uniformly were cooler than batteries on the top, and significantly so. And it's rather encouraging to see the difference, a very clear difference in performance. And just from this alone, I can conclude that a vent makes a significant difference in the cooling performance of one of these systems. But again, I'm looking to validate. The purpose of this was to validate my simulation for later investigation into a full-size system. So looking at experimental and simulation, experimental in the green, yellow representing simulation, you'll notice that in general, temperatures tend to align between experimental and simulation. There is some deviation on the scale of 2 to 3 degrees Celsius. But more importantly, the general profile of battery temperatures along each line, being 1 through 4, 5 through 8, 9 through 12, and 13 through 16. Those align very well, and they follow similar trends, which is really encouraging. And I think this is adequate justification that the simulation is a valid method of analysis, because clearly it represents or aligns well with realistic or real life output. So going into the full-size model, there again is that same default design. There's the Vortex generator design, and then there's the vented model design. And here we're seeing the default model design. That same air is ported in through the bottom, it comes through, and it doesn't diffuse, unfortunately, until it hits near the rear of the case, and then comes back up and is ported out. So obviously, it's experiencing many of the same problems that the experimental default model experienced, where batteries towards the front are not adequately receiving airflow and thus become very hot. The Vortex generator model shows similar behavior. However, you may notice that there are small vortices caused by the Vortex generators, which are mounted towards the back of the model. Unfortunately, I don't believe that Vortex generators in the front really received a high enough velocity bulk flow to really make a difference, but some of these towards the rear did. And I've blown up the view here. However, in general, the total behavior of the flow tends to mimic that of the default model with little variation, at least from the naked eye. The full-size vent model is shown here. And if you're thinking this one looks awfully blue, I should say that I had to change the resolution on this one just to properly show the vents. But you can see that those high velocity air jets are being produced. However, they don't really reach the top rack. But the most encouraging result coming from this model is the fact that air is properly being distributed to all batteries, no matter where they are in the line, whether they're in the front or the rear. All batteries are getting at least some cooling from air. So looking at the summary of results, the average battery temperature decreased for both Vortex generators and vent, and so did the maximum temperature differential for Vortex generators and vents. And so from this, I can conclude that both had a positive effect on the cooling performance of the system. So implementing something such as Vortex generators or a vent more successfully, but the Vortex generators did cause a noticeable decrease in the average battery temperature and in the presence of temperature differentials. And while I said previously that it's hard to see the effect that the Vortex generators are having on the total flow, they obviously did have some effect looking at the numbers. And so here are the 3 different models, and their temperatures assigned for each battery are plotted here. So you can see that the default model, batteries in the front of the case, namely 1, 5, 9, and 13, always show elevated temperatures, whether they're on the bottom of the rack or on the top. But the Vortex generator model was able to decrease these temperatures in batteries 1, 9, and 13, and then even barely in 5, but not significantly. So just looking at this, it's obvious that the vortex generators did successfully distribute more airflow towards the front of that case by simply disturbing that laminar air inlet flow. And then the vented model, which is in light green, I'm hoping you can all see that. Batteries on the lower rack, which are 1 through 8, all have the lowest temperatures and very little in terms of temperature differentials, whereas batteries on the top rack do have slightly elevated temperatures, but more encouragingly is that there's really not many temperature differentials aren't present in the way that they are for, say, the default model or the vortex generator model. So that was the performance of the different models under identical input conditions. After that was done, I started to treat inlet air velocity as an independent variable to really see the effect that it has on battery temperatures. And what I wanted to do was look at the effect it had on the two models that were most contrasting, namely the default model and the vented model. So for varying the inlet air, I found that in order to achieve an average cell temperature of under 30 degrees Celsius, the vented model was able to do that with 24% less air inlet flow in comparison to that default model. So that's 24% less air that needs to be input. And while that might not sound significant, using fan affinity laws, correlations between air inlet flow for a single fan can be drawn. And it's actually a result of the cube of the ratio between two inlet flows. And so assuming the same system is being operating, that 24% decrease in air input corresponds to a 65% decrease in required cooling energy that needs to be used to power a fan. And this is I need to be clear, this is a theoretical maximum. In reality, it would be lower, but if you account for the fact that many battery cooling systems have to run 24/7 all year, even a 10% decrease in input fan energy could be significant, especially taking into account how large some of these stationary battery systems are. So some of the outcomes from my research, I recently published a literature review on the state of stationary battery thermal management. I had mentioned previously that there had been a lack of research on these topics, specifically in contrasting with how much research there is with electric vehicles and their batteries and how much research has gone into that. There's almost none for stationary batteries, and really trying to put together a review of the state of this field in academia was the paper that I was able to publish. The investigation that I just went over, the active cooling assessment of the different designs and the validation of a simulation model is significant to the research. And the identification of those two strategies, namely the vortex generators and the vent plate, both of these are well-known methods for increasing heat transfer or better distributing cooling load, but neither of these had been done in application to stationary batteries. And I think that's significant and could potentially steer future research on these topics. And then I'm currently working on compiling the previous 2 points, the validation and the identification of those two cooling designs into another paper, which I hope to publish in the coming year. So future research, there's obviously some questions that come up or new ideas that have arisen in my mind from this analysis. And one is I'd like to incorporate a more comprehensive heat generation model or battery thermal model. Looking at these batteries or the figure shown below, you'll notice that batteries have uniform temperature. The color of each battery represents the temperature. And really, there's no gradients represented across these batteries. And for a full-size stationary battery, that's not something that can just be assumed. So in future analysis, I'd like to perhaps incorporate a more comprehensive thermal model for these batteries, such as the internal chemistries or what the actual materials, outside materials are made out of, or perhaps even some of the nuance in their geometries or constructions. I'd like to do that in the future. I don't think this one applies to me, but full-size prototype construction, either of this model or of a similar model to really validate a full-size simulation, whereas the full-size simulation has been validated using that scaled down model. A much more, it would make a better case for the use of full-size simulation if the full-size simulation could actually be validated using a full-size prototype. But that's future work. And then revision improvement of vent and vortex generator designs. There's actually been a lot of research on vortex generator designs and geometry and placement. And I really took one design and stuck with it. But I think that the vortex generators could be improved by changing their placement, such as placing them directly at the inlet, perhaps giving them an angle so that they create vortexes. There's even different types of vortex generators that have rectangular construction or a curve to them. So there's many different designs that could be done and see their effects on the cooling system. And even for vents, there's been parametric studies done on vent design and how to effectively accomplish that. And then lastly, I think it'd be important to perhaps do analysis to a specific existing battery system application, such as batteries used in alternative energy storage or a UPS used in telecommunications. Obviously, these two batteries, depending on their use, will have different operational characteristics and different, probably use a different technology, either lithium ion or lead acid, and really getting it up close and building a simulation that's analogous to a pre-existing design and its operational characteristics. So that is my presentation. I'm not sure how I'm doing for time, but I'd like to open the floor up to questions if anyone has them. And I was told there'd be a delay.
So, Martin, thank you very much.
Yes.
So let me start a question while we wait for the transfer. So
Okay.
one of the questions I have is, I'm new to this area. It's a very fascinating topic. The question I have is, the temperature that you were dealing with were always in 30 to 45 degrees Celsius. And that's the range you are working with. Now the question is, what is the standard average temperature that we use in like Alaska? Because 30 looks very hot for me, especially when you look at degrees Celsius. So how are we maintaining the battery in Alaska?
Well, for the most part, these battery systems are all contained indoors. Again, I'm not aware of any difference in standards applied to Alaska, but I imagine if they're being used indoors, it allows for opportunities for passive cooling by extracting air from the outside. But in general, I don't know of any active air cooling systems that are being implemented. There are occasional instances where battery systems are enclosed in a cabinet and then placed outside. But I believe this is, in general, that practice is avoided in places with extreme temperatures, either too hot or too cold. And I think Alaska definitely falls into the latter category. So I think that they require air conditioning systems and to be placed inside, so cooling systems.
Okay. Perfect.
Yeah.
Because I thought in Alaska, the heating it should be the other way around, because we are like more worried about heating it to an extent. Yeah.
Yes. In general, I think that's more of a regional problem, keeping those temperatures up, but I think generally in order to avoid cold, they're kept indoors.
I agree. Thank you.
Okay, that is actually looking like all of the questions that we have. It looks like you explained it really thoroughly, so thank you very much.
All right.
Okay, well, thank you so much for your presentation. It was very interesting, and we'll go ahead and
Thank you for having me.
conclude today. Thank you so much. Have
All
a
right.
great weekend.
Thank you, Martin.